Okay, so let's take a look at see how we're going to graph polynomial functions. What I have on the screen are steps that are recommended by the author as far as how we can do this. Of course, these recommendations are not unique in that in another textbook there may be 7 steps. Okay, but these are pretty adequate for what we want to do, and I'm going to follow these steps. The one additional step that I like to add to this is that if you can determine whether the function is even or odd, that's also going to help us graph these functions. Remember, even functions are symmetric with respect to the y-axis, and odd functions are symmetric with respect to the origin. Okay, but for now, let's go ahead and try to graph this function. In our first step, we're going to look at the end behavior of the graph of the function. Now, I did mention about the end behavior in the previous lecture on section 4.1, where we discussed polynomial functions. So you might want to review that lecture if you need a refresher on that. So to determine the end behavior, we're going to look at the leading term. And remember, the leading term is when you multiply x times x to the third, and x, the degree on x plus 2, by the way, or the multiplicity of this factor is 1. So that means that's just a linear factor. So degree on x is 1. The degree on x in the second factor is going to be 3. So degree of this polynomial n is 4, and the leading term a sub n is -2. Therefore, the end behavior is going to resemble -2x to the 4th power, right? X to the 4th power. Now, our x to the 4th is going to look like this. And this is x to the 4th. And these functions, we looked at power functions also earlier in the earlier section, section 4.1, the previous lecture to this one. So this is the graph of x to the 4th, extremely flat around 0. The negative will cause a reflection, so this graph is going to look somewhat like this. And we are only interested in the end behavior of the graph of the function that we're doing with respect to the basic power function, -2x to the 4th. Now, the end behavior would be this. And that means as x goes to infinity, the function approaches -infinity. As x approaches -infinity, the function still approaches -infinity in both cases. All right. So far on my graph, this is what I'm going to do to the right. See, I'm going to put the arrow down and arrow down. So that's all we get from that step 1, the end behavior of the graph of our function. Now, in step 2, it says find the x and the y intercepts. All right, so let's do that. The y-intercept, that's pretty easy. That's when you put in 0 for x. So in other words, you do f at 0. So that's going to be -2 times 0 plus 2, 0 minus 2 cubed. And the whole thing is going to be negative times negative positive. That's going to be 32. Right? -2 cubed is -8 by 2 by -2. That's going to be 32. So here's, let's say 32. Okay, it's going to be right there. I just picked a random point on the graph. So here's 0. Again, this point is 0, 32. The y-intercept. The next thing we need to know, we determine the y-intercept. Well, let's do the x-intercepts. For the x-intercept, we're going to set the function equal to 0, f of x equals 0, and actually solve for x. And because we have the factored form, I'm going to set the factored form equal to 0. Okay, the factored form. Now, by 0 factor principle, each of the factors could be 0. And of course, a constant -2 isn't 0, so that's not going to participate. We're just going to say x plus 2 may be 0, or x minus 2 cubed may be 0. All right, and we get a couple of zeros, -2 and x minus 2 could be 0, so x is 2. All right, and those are my x-intercepts. I'm going to have it at 2 and -2. Let's say this is 2 and -2. We're going to be equal distance on the other side of the origin. So those are 2 and -2. And then step 3, determine the real zeros of the function, their multiplicity, and use this information to determine whether the graph crosses or touches and bounces. And remember, if the degree of the factor is odd, it's going to cross. If the degree of a factor is even, it's going to touch and bounce. In this case, the degree of x plus 2 is 1, so is the degree of x minus 2. So both of these x-intercepts will be crossed, and our zeros here, the zeros, remember, those are what make each factor 0, which we found them here and in here. The zeros are 2 and -2. Each of those have multiplicity of 1. Again, means we have just one factor with those 0 each. So both cases, the graph is going to cross. So it's going to cross like a line, y equal x does. It can cross this way, or it can cross this way, it can cross this way, or it can cross this way. And then we're going to go through elimination process on how I determine. We're going to rule out some of the possibilities and stay with the other one. Alright, therefore at 2 and -2 it's going to cross. That means at x equal 2, x equal -2, function crosses the x-axis. So the question is, how is it going to cross? Is it going to cross like this, like this, like this, or like this? Now, step 4, determine maximum number of turning points. Remember, the maximum number of turning points is n degree of the polynomial minus 1. This one is, oh, sorry, it looks like I removed the cubed here. I was looking at this, how did I get 4? So, actually, what I said earlier works still. I got lucky because both of these factors have odd exponents. So everything I said here still holds down here. But please be careful. Unlike me, do not erase that 3. All right. Now, the thing that I do need to change, however, is this part, right? Because at x equal to 2, that's the 0 that came from this factor. The multiplicity is 3, correct? So it's going to cross like x cubed does, not like a line does. So that means it can either do this, or it can do this. The question is which one? And we'll answer that in a few moments. Now, having gone through the steps again, maximum number of turning points for this is going to be 3, right? 4 minus 1. I'm just going to put that max turning points is going to be n minus 1, or 4 minus 1, or 3. So you can have 3 turning points. We'll keep that in mind. And what is a step 5? Step 5 says use information 1 through 4 to draw a complete graph of the function to help establish the y-axis scale. Find additional points on the graph on each side of the x-intercepts. Okay, perfect. Now let me show you how I'm going to do this with as few points as possible. Now, as far as ruling out which one of these, for instance, because remember the end behavior is going to look like this. Therefore, if the function is going to end up down here, it is impossible for it to go in this direction, correct? It's going the wrong direction. It has to go in this direction. So that, in essence, rules out this possibility. The graph cannot cross this way. Therefore, it looks like this is the part of the graph that we need for below the x negative 2. Let me go like that. Okay. Now, it's, let's see, and negative 2, oh, it's going to cross like a line does a linear function. So it's really going to go like this, more like this. It's going to cut right through it. Because x plus 2 is a linear factor, so it's going to go like a line does. It's going to cross like a line does. All right, now x minus 2 cubed, this one, again, if the function behaves this way, well, that's opposite of where it's going. When x is positive and going to infinity, remember the function has to go to negative infinity. So this part is ruled out. If that is ruled out, then we're going to eliminate this possibility. All right, so what else remains? This is the only choice here, right? The graph has to do this. So we're going to make it work like that. Okay, and that's that part of the graph of the function. And then it has to curve around, come back, and it's going to go through. And there you have it. That will be the graph of this function. Now, an additional point here. So, for example, let's say if I do negative 1. Okay, here this is negative 2, this is negative 1. If I look at f, this is part 5, step 5 of the guidelines. I'm going to do f at negative 1. When you plug in negative 1 into this function, we get negative 2 times negative 1 plus 2 and negative 1 minus 2 cubed. Okay, what did I do? I plugged in negative 1 in the original function. All right, and when we do, all of this should end up being 54. And that's this point right up here, negative 1 and 54. That seems to be perhaps the maximum. I'll make a comment about max and minimum here in just a few moments. That's maybe the maximum. I don't know. Okay. And then another point, for example, an additional point to the left of this 0 would be f at 1. And when you put 1 in our original function, we're going to get 1 minus 2 cubed here, and the whole thing ends up being 6. Therefore, f at 1 is going to be 6. That's this point right here. That's 1 comma 6. All right. Now, and we're done. That's the graph of the function. That's the best we can do. Remember, max turning points were 3. We have 1 turning point. That's it. The turning point is where you have a peak or trough. That's when the function changes from increasing to decreasing and vice versa, decreasing to increasing. And there we have that one. Otherwise, right in here, see, that's not a turning point. That's just a continuation of the graph. All right. Now, the comment I want to make is for the location of the extrema, the max and the minimum. In this course, a pre-calculus course, we don't know if that is a maximum. Okay. And the minimum, clearly there is no minimum because the arrows go indefinitely south to negative infinity. So for us, we just plot the points, and we get the whereabouts of the peak and the valleys on the graph. Now, in calculus, first semester calculus, there will be procedures that will actually determine the exact coordinates of the extrema, that is the max or the minimum of the function. And not only that, it also shows where the curvature changes. So for instance, if you look at this part of the graph, it looks like it's curved downward here and it's curved upward here. So the exact transition from down to up, that point will be determined in your first semester calculus. Okay, so for now, again, we don't know what those key turning points are and the points where the curvature of the curve, the graph is going to change. All right. And there you have it, the end of our first example. Now let's take a look at another example here. In this next example, let's say I have a function f of x, and this function is x plus 1 squared and x minus 2 squared. So we can immediately see that the degree of this polynomial n is 4, right? 2 and 2 you add, you get 4. So that means n minus 1, 4 minus 1, 3 is the, that's going to be the max number of turning points this thing could have. The graph of this function could have at most 3, no more than 3. Could have 3 or 2 or 1 or none. We'll see about that when it gets closer. Now the end behavior, right? That's very important, folks. The end behavior is extremely important. The end behavior is, for end behavior, the leading term. We need to know the leading term, what it is. Our leading term is going to be, because there's no number in front, so a is 1. So it's going to be 1 times, and you only look at the first term in the first factor with x, and first term in the second factor. That would be x squared, so that's x to the 4th. The leading term of this polynomial is 1x to the 4th, or simply x to the 4th. Okay, so what does that mean? That means for very large, very small x values, this function is going to graph like x to the 4th does. And remember, x to the 4th was our power function. We looked at those in section 4.1. And all we get from this part, this step, is the end behavior. Okay. So for our graph, for our own graph, the graph's going to end up in the first quadrant when x is very large, first quadrant. And for x very small, going to negative infinity, the function goes to infinity. So I'm just going to write that. As x goes to infinity, gets very large, the function will get very large. And as x goes to negative infinity, the function still remains very large. Those are what we call the end or extreme behavior of the function. All right, so now I'm going to put that on my coordinate system. All righty, so here it is. See that? That's all we get from that step. The extreme behavior of the function. These going to infinity in both directions of x. Very large x, very small x. And then we're going to find the xy intercepts. Remember, the easier of the two is the y-intercepts, because you just put in 0 for x. Do f at 0, and f at 0 would be 0 plus 1 squared, and 0 minus 2. Of course, that was squared also, before I erased it accidentally. There you have it. 0 minus 2 squared, so that's going to be 1 times 4, or just 4. So this is going to cross the y at 4. I'm just going to go right up here. That's the height of 4. That's the y-intercept. Let's do our x-intercept. Once we have the x-intercepts, we have the zeros, right? So x-intercepts and zeros kind of go hand in hand. To find the x-intercepts, we set the function equal to 0. That means the factored form, x plus 1 squared, times x minus 2 squared must be 0. And by zero factor principle, either factor could be 0. Don't worry about their multiplicities. Because what we can do is this. Let's say for this one, I can take the square root of both sides, and that reduces it just to a linear factor. Okay. Of x minus 2. So we just simply set the linear factor equals 0. We'll pick up a couple of x-intercepts, or a couple of zeros actually for this. These are the zeros. So the x-intercept as a point is going to be -1, 0, and 2, 0. Remember, these are points that must have both x and y. The zeros, one occurs at -1, right in here. The other one occurs at 2. Now, once we determine the zeros, this is another important part. The zeros are -1. We need to determine the multiplicity. The multiplicity will tell us how the function behaves near those zeros and whether it cross or touch and bounce from it. So remember, the -1 came from this factor, so it has a multiplicity of 2, right? And why has it multiplicity of 2? Because the exponent is 2. So is the next one. Each of those have multiplicity of 2. -1 multiplicity of 2, and also 2 has multiplicity of 2. Both of those. All right. Now, the implication we have, because even multiplicities, it has to touch, and it has to touch. And remember, I say touch and bounce. It's not going to go through. Because multiplicity is 2, so it's going to touch and bounce like a parabola x squared does. Okay. And there we go. At this point, here's what I know. It's going to touch and bounce here. It's going to touch and bounce here. Now, the other part of that is this. Well, how do I know it's not going to touch and bounce in this manner? Well, those we can rule out easily, couldn't we? Look at this one. If it touches and bounces this way, this is going to -infinity, but we got to go to infinity, right? So it's going the wrong way. This is ruled out. There you go. As simple as that. And look at this portion. Again, same token. If it does that, it's going to -infinity, wrong direction, where it's got to go to infinity. So those are the ways that I can rule out the possibilities of touch and bounce at a point. Now, for this one, I'm going to actually just choose another point here, for example 1, and then f at 1 is going to be 1 plus 1 squared, 1 minus 2 squared, and that's 4 times 1. -1 squared is 1. 4. Wow, that's interesting. The function is at 4. Now, because the graph of this function, it has a degree greater than 1, so it's not going to do anything like this. Okay, the point being, I'm not going to have a flat line here connecting these two. It's just not going to do that. So, and this will suggest to me that it's simply going to go higher than 4, and then it's going to come back and go through 4 once again towards the x-intercept, and then it's going to shoot up to infinity. And there you go. That would be this portion of the graph. The other portion of the graph is going to go like this. And there you have it. Now, if you suspect symmetry, we could actually foil this polynomial and see if we get some kind of a symmetry here. Okay, but again, this is good enough for our work. And there we have the graph of this function. Okay, and let's see. That's about all we want to do with this function. Let's take a look at another example. So in this example, or next example, suppose I want to now graph a function that is not in factored form. X cubed plus x squared negative 12x. So if a function, polynomial function, is not in factored form, we need to factor first. We need to factor. So our factoring skills here, we always look for monomials, a single common GCF. The greatest common factor here is x. So we're going to remove x. That'll give me x squared plus x minus 12. Once you remove what's common, remember when you remove the GCF, we literally take out the x. That's why I just removed the x. And then you divide x cubed by x, x squared by x, 12x by x to get the remaining terms within parentheses, these. All right, now we need to factor the trinomial. These trinomials, for most parts, going to be factorable. And we're going to set them up as a FOIL. The first terms are going to be x. I'm looking for two numbers whose product is negative 12, and the product is negative 12, and the sum, this is the product of two numbers. The sum is 1, the coefficient on x. Okay, and those would be plus 4, negative 3. Product negative 12, and 4 minus 3 is 1. Okay. And there you have it. So we do have the factored form, and now we can go through those steps like the previous one. Let's look at the end or extreme behavior. The extreme behavior is given by the leading term. In this case is going to be 1, and that is what a is. A is the coefficient on the leading term. A is 1. So it's going to be 1 and x cubed. In fact, there you go, that is your leading term. So it's just x cubed. That means the function is going to behave like x cubed does. So there you go. That we have from our power functions from, again, previous section. Therefore, x going to infinity, function has to go to infinity. X goes to negative infinity, the function has to approach negative infinity. Again, it means those endpoints. We don't care what happens between them. It's just look at very large and very small x values is all we care about here. Okay, so got that figured out. Next, we're going to do our xy intercept, the y-intercept. Do f at 0, so that's going to be 0 cubed plus 0 squared, negative 12 times 0 is 0. I plugged into the original function right there. Therefore, the y-intercept is 0, 0. That means x-intercept, one of them has to be 0, 0 also, because the graph goes through the origin. So it's going to cross both y and the x-axis. Now the x-intercept, for this, we set the function equal to 0, and it's easier to set the factored form equal to 0. That means x plus 4, and x minus 3 may be 0. Each of those could be 0, so here's x 0, as suggested by the y-intercept. So that's when x is 0. This next factor is 0 when x is negative 4, and the one next to it is 0 when x is 3. Those are the x-intercepts. Correct. And then from those we get our zeros. The zeros, each factor here has multiplicity of 1, right? X plus 4, x minus 3, those. Each of those you can rewrite with an exponent of 1. So for each of these intercepts, for each 0, the function will cross. So f will cross all zeros. And the way it will cross, because they have a single degree, they're linear, it will cross just like a line does, this way or this way. Okay, it's not going to do this. It's not going to be doing this. That would be for x cubed, x fifth. And this is just for x. Okay. Now, once we have that, it will cross zeros. Let me just add like y equal x does. Because again, each of these have an exponent that is 1. All right. And we got the leading term, we got the x-intercept, y-intercept, we got the zeros. Oh, turning points. Turning points is going to be the degree. This was a third degree, correct? Yes. X cubed. This is going to be 3 minus 1. n minus 1. And 3 minus 1, at most 2. So you could have 2, 1, or none, at most 2. Remember our previous example, by the way, I never mentioned this one. Let's look at the turning points. This one had maximum of 3. Our previous example, check this out. Here's 1, 2, 3 turning points. Okay, that's just the previous example. Now for this one, we could have at most 2 turning points. Now let's put all of this information on the graph of the function. So let me draw my coordinate system first. And there is my coordinate system. Now the points of intercepts are 0. These are my x-intercepts, right? 0, 3, negative 4. So let's say this is 3. And this would be negative 4. Okay. And we know the extreme behavior. It's going to go like this. It's going to go like this. Now, the elimination portion. Each of these could be crossed either this way, this way, this way, this way, and this way, and this way. So let's go from left to right. It is impossible for the function to cross negative 4 like this, because notice it's going to infinity in this direction, which is the wrong direction. We want it to go in opposite direction. Therefore, this is ruled out. So at this point, I'm going to make it cut right through this way. Okay, and then if it goes like this, well, if it continues this way, it's going to miss this intercept, right? So it cannot come back, touch, and go this way, because the 0 at negative 4, remember, it does not touch and bounce. So this is ruled out. Okay, therefore, the function has to come up, turn around, and go right through. Now, as it goes right through, like this, it is impossible for this configuration to happen, because the function has to come back, go up, cross, and come back here. 2 things happen that are not supposed to. 1, it's going in the wrong direction. 2, it will create another x-intercept there, which doesn't exist. So that's ruled out. This portion is ruled out. And now we're looking at the other portion of the graph. That's going to have to behave like this. Now, exactly where it's going to turn, the low point here, I don't know. Exactly where the peak's going to be before it goes through, I don't know. Again, we will know these in calculus, because we do really need the knowledge of calculus in order to find the maximum value of these functions. And that's why it is so pivotal to learn things as concrete as possible as we can, so we'll have much easier time in calculus courses and beyond. All right, and there you go. For us, that's a good good graph. You're welcome to, for example, I haven't, but you can do f at 1 and see where the function is. It's going to be somewhere in here, right? I bet you the answer is going to be negative. And do f at, negative 1, negative 2, something like that, f at negative 2, bet you that answer is going to be positive. And that just gives you a couple of points, additional points on the graph of this function. Okay, so there you have it, and we're done with what we wanted to do here. And we have completed the graph of this function. Now, let's do one last one here to get practice with graphing functions. Now, for this one, again, I'm going to have a function. And this time, we're going to have, again, the polynomial form, not the factored form, just so we can practice factoring here a little bit. We don't forget our factoring skills. Now, if you recall, by the way, a real quick, just-in-time review of factoring. When we factor polynomial, we always look for GCF, greatest common factor. which is what I did up here. Remember, the GCF of that expression, of this expression, was x. So we removed the GCF. So we always look for GCF. And then we look and see if the polynomial is in ax squared plus bx plus c. If a polynomial is like this, then chances are the factored form is going to be a binomial, another binomial here. And then certain special products come in. For example, if I have difference of two squares, the special product is going to be a plus b, a minus b. That comes in handy. And we also have a formula for difference of cubes. Again, this is just a quick review of factoring. It's going to be a squared plus ab plus b squared, the factored form, if you recognize difference of two cubes. And we could have sum of two cubes. For sum of two cubes, the factored form will be a plus b, a squared minus ab plus b squared. And if we factor them using these formulas, the cubes, these two polynomials, these two will never be factorable. We call them prime polynomials. So these are the factoring skills that we bring with us to this course. And one last one is when the expression has 4 terms, like my example I made up here. If the expression has 4 terms, typically we factor by grouping them, and that's what we're about to do. Okay, so factor for grouping. I need to come up with a pair of groups. So I'm going to group the first two, the last two together. Once you pair these, we need to remove the GCF. Now, before I actually remove GCF, I see that there is a GCF. There is a greatest common factor between all 4 terms, right? All 4 terms have x in common, and all 4 terms have even coefficients. So they got to have at least a 2 in common. And because 2x to the 4th, the GCF is indeed 2x. So I'm just going to remove 2x here. The greatest common factor is 2x. And what's going to be left over is x cubed, that's coming from the first term. Divide 2x to the 4th by 2x, you get x cubed. Next, you divide 12x cubed by 2x, you're going to get 6x squared. Divide 8 by 2, you get 4x squared by x. We got x. 48 by 2, that's going to be 24, and the x by x is 1. And there we have this one. Okay, so we have 2x times that polynomial. Now, because there are 4 terms here, I'm going to try factor by grouping them. And let's do that. Now in here, I'm going to group, let's say, first 2, last 2 together. From the first 2, the GCF is x squared in that group itself. I'm going to factor x squared. That will leave me with x plus 6 from the first group. And from the second group, I'm going to factor negative 4. That's going to make it x plus 6. And that's actually that was a good grouping. The reason, because now we recognize a common binomial factor, x plus 6. So we're going to remove now x plus 6 as a common factor. From this expression, we only have x squared. And from the one next to it, we only have minus 4. And there is the factored form within the brackets. And on the outside, we have 2x. At this point, because everything is being multiplied, we can simply let go of the brackets here. Okay, and that's what factoring did for us. Now, x squared minus 4, check this out. You see that? X squared minus 4 is a difference of 2 squares. So that could be factored further. I'm going to write it as x plus 6. And then x squared minus 4, that will be x minus 2, x plus 2, or x plus 2, x minus 2, doesn't matter. The order of those don't matter. And there now we have the full factored form of this polynomial. Remember, the leading term from the get-go leading term, we need that for n behavior. Our leading term is 2x to the fourth. So we can determine right away. The degree is 4. Degree, which is n, is 4. So that means my turning points will be at most 4 minus 1, 3 at most. Again, it could be 3, 2, 1, or none. Got the leading term. Oh, extreme behavior. For extreme behavior, we look at the leading term. We look at this term. 2x to the fourth. Well, x to the fourth looks like so. Right? That's our power function with an even exponent. So we can write now as x goes to infinity. And 2, by the way, here, for what we're doing here, 2 doesn't play any role here. But if that number 2 is negative, we do have to remember to reflect. And that will change the n behavior. So for this work, you only look whether the leading coefficient is positive or negative. If it's positive, just ignore it. If it's negative, reflect the graph. As x goes to infinity, x gets very large, the function approaches infinity. That's what this arrow means, by the way. Think of this as the word approaches. As x approaches negative infinity, the function approaches means it goes towards infinity. All right, so we managed to do the extreme behavior as well, the n behavior. Now the other standard stuff, the y-intercept, we do f at 0. Maybe easier to go into the original, right in here. Plug in 0, 0, 0, 0 there. So you get 0. F at 0 will be 0. That means 0, 0 is the y-intercept, therefore x-intercept, one of them anyway, is 0, 0 as well. Now for x-intercept, we set the function equal to 0. And for us to set the function equal to 0 means practically we have to solve that equation, right? And that is where the factored form comes in. And so I need to find the zeros of the function for the x-intercepts. I'm looking at the factored form here. So bring that down here. Your x-intercept is going to be x equals 0, x equal negative 6, x equal 2, and x equal negative 2, right from here. See what makes each factor 0. And these are the zeros. Now, every one of these zeros, by the way, has multiplicity of 1, 1, 1. So that means the graph of the function is going to run through each of these. Okay, let me just, for completeness, put the zeros. The zeros are 0, negative 6, 2, negative 2. Each multiplicity of 1. That means they repeat only once. And remember, if they repeat only once, means a graph crosses the zeros. Every one of them, it will be crossed. And the way it will cross it, because this degree is 1, it's going to cross like the line crosses, either this way or it crosses like that. It's not going to bend and go through like x cubed or x to the 5th and higher powers of power function do. All right, I think we're good. We determined the turning points at most 3. So let's go ahead and put this information on the graph of our function. Let me bring my coordinate system first. Okay, so I got my coordinate system here. First, I'm gonna display the extreme behavior on there, just like, oops, sorry, I didn't do this one right, just like x to the 4th. So that's going to be the extreme behavior, correct? Now let me show the intercepts. 0, let's say this is 2, this is negative 2, and negative 6 would be, let's say, here. All right, so this is negative 6. This is negative 2, 0, and 2 here. All right, and remember, every one of these has to be crossed either this way or this way. This way or this way. This way, this way, this way, this way. Now we can go through our elimination process, right? So for example, the function cannot cross negative 6 the way I have right now, because it's going in the wrong direction. This is ruled out. So it has to come through and cut through like this. Okay. Now negative 2, again, it has to go through. So this is, oh, sorry. I didn't mean to do that. Hold on, let me bring my coordinate back. Alrighty, sorry about that. So I have my coordinate back. And let's continue on. So at negative 2, right? This was negative 2. Right about here. So again, we ruled out this possibility because it's going the wrong direction. So it has to go, and this thing has to come back and cut right through this point at negative 2. Now, to go through 0, again, this possibility is ruled out because it's going to go the wrong direction. In order to go through, it has to go this way. Let me remove that one. So it's going to come back and go right through. See how I went through that? I did not wiggle. So it has to go right through like a line does. And then again, this option is out because it's going to negative infinity. It has to go to positive infinity. Therefore, it has to come back, right? It has to come back at some point and go through like that. Now, the exact turning points, coordinates, I do not know what those are. Correct? Most likely this is going to come down and go back up so it can cut through a little better. There you go. Now it's truly going through like a line does. All right, and same thing for this part. Now this is a fairly realistic portrait of the graph of this function. There you have it. I don't know the low point, the high point, and the low point. Now look at turning points. Turning points, remember, at most 3 we set up there. And we do have indeed exactly 3. 1, 2, 3 turning points. These peaks and valleys, we'll find the coordinates in the first semester calculus. So with this, we are done with the graphing of polynomial functions. So please, if you need to, go back up. One thing I want you to do is practice your factoring for sure, because that's a skill that's very important going forward. Even when we go to trigonometry, factoring is going to be extremely important. All right, so with that, we are done with this lecture. Again, thank you for watching and good luck.